Hey everyone, and welcome. Today, we're going to dive into a single mathematical idea that, believe it or not, is like an invisible blueprint for our modern world. It's a concept that's hiding in plain sight, and it's quietly shaping just about everything around us. So let me just start by asking you a question. What could possibly connect the way you search on Google, the bridges you drive across, and the thousands of photos you have saved on your phone? I mean, they sound completely unrelated, right? Well, it turns out they are all built on the exact same mathematical foundation. Think of it like a hidden architecture, a secret recipe that knows how to pull out the most important, the most critical information from really, really complex systems. Okay, so let's get into what this blueprint actually is. It all comes down to two core ideas: eigenvectors and eigenvalues. Now, I know, those names sound a little intense, but trust me, the actual concept behind them is surprisingly visual and honestly pretty intuitive. Okay, picture this. You've got a sheet of rubber, like a big elastic square. And on it, you've drawn a ton of little arrows. We call them vectors, all pointing in random directions. Now, what happens if you grab the edges and stretch that sheet? Well, almost every single arrow is going to get longer, and it's also going to point in a new direction. But, and this is the cool part, there's going to be at least one special arrow that, even though it gets stretched longer, it keeps pointing in its exact original direction. That special unchanging direction, that's the whole key. So that special arrow, that special vector, that's what we call an eigenvector. And the name actually gives us a big clue. The German prefix eigen literally means own, as in this vector has its own special direction that it holds onto no matter what. And the number that tells us how much that eigenvector got stretched or maybe even shrunk, that's its sidekick, the eigenvalue. It's just a number, a simple scale factor. And this whole beautiful idea gets boiled down into one simple, elegant equation: TV equals lambda v. All this is saying is that when you apply some transformation, that's the t, to an eigenvector, that's our v, the result is the exact same vector just scaled by a number, its eigenvalue lambda. The transformation doesn't mess with its direction, it just scales it. That's it. So let's really drive this home. When you apply a transformation, almost every vector you can think of gets knocked off its original path. Both its direction and its length change. But eigenvectors, they're special. They are these stable, unshakable directions within that transformation. They're the lines that only stretch or shrink, but never, ever change the direction they're pointing. Okay, so why is an unchanging direction so important? This is where things get really cool. Let's look at our first huge, real-world application and see how this one idea literally organized the entire internet. Yep, we are talking about Google's original, game-changing PageRank algorithm. You know, back in the early days of the web, the big problem was, how do you figure out which of the millions and millions of pages are actually useful? The genius of PageRank was to look at the entire web as this giant interconnected network. Every single web page is a dot, a node, and every hyperlink is a connection between two dots. A link is basically a vote of confidence from one page to another. But, and here's the crucial part, not all votes are equal. A link from a major, reputable site is worth way more than a link from some random page. And this is where it all connects. If you treat that whole web of links as a massive mathematical transformation, you can find its eigenvector. The most important one, the one with the biggest eigenvalue, is called the principal eigenvector. And guess what it represents? It points directly to the pages with the most influence, the most authority. That eigenvector is the page ranking. It's the stable underlying structure of importance on the web. Mind-blowing, right? Okay, let's shift gears from the web to the visual world. Every single day, we create billions of photos. How in the world do we store all of that data without our phones and computers completely overflowing? Well, the answer, once again, comes back to our friend, the E-vector. See, a high-resolution photo is just a massive amount of data, information for every single tiny pixel. Storing all of it is super inefficient. The whole key to compression, like the JPEG files you use every day, is to intelligently throw away the data that your eyes won't really miss. But how does a computer decide what's important and what's junk? This is where a powerful technique called principal component analysis, or PCA, steps in. PCA uses eigenvectors to find the principal components of an image. You can think of these as the main directions of information in the picture, the things that capture the most important visual data, like the strong line of a horizon or the curve of a face. By keeping the information along these key eigenvector directions and just tossing out the less important details, we can shrink an image down dramatically while keeping it looking sharp. And the applications, they don't stop there. Not even close. In fact, they're so widespread, it's almost hard to keep track. So let's do a quick lightning round of just a few more places this invisible blueprint is hard at work. In structural engineering, every single bridge or skyscraper has natural frequencies that it just wants to vibrate at. Eigenvectors are used to find these exact frequencies, these modes of vibration. By knowing what they are, engineers can design structures that won't dangerously resonate with forces like strong winds or an earthquake, preventing a total collapse. It's literally a lifesaver. Now let's go from massive structures to the microscopic world. In genomics, scientists are looking at the activity of thousands of genes all at once. It's just a sea of data. Eigenvectors help them cut through the noise and find the most important patterns, like which groups of genes always seem to turn on and off together. This helps them identify different subtypes of diseases, like cancer, which can lead to much more targeted, effective treatments. And yes, this even applies to our social networks. A concept called eigenvector centrality, which has a direct descendant of PageRank, is used to find the most influential people in a network. It's not just about who has the most friends, it's about who is connected to other well-connected people. This is huge for everything from figuring out who the key influencers are for marketing to spreading critical public health information quickly and effectively. So, from ranking the entire internet, to keeping our bridges standing, to compressing our family photos, eigenvectors give us this incredible power to find the essential, the stable, the most important features buried inside incredibly complex systems. They truly reveal the hidden structure of our world. And it really just leaves you with one final thought. What complex system will we ask them to unlock for us next?